Heat. It's the reason your coffee gets cold and your ice cream melts. It's flowing all around us, all the time, completely invisible. But how does it actually move through the solid walls of your house or the guts of your phone? Today, we're going to pull back the curtain on the physics of heat conduction and make that invisible flow, well, visible. Let's jump in. So here's our game plan. First, we're going to look at heat flow as a kind of invisible obstacle course. Then we'll see how layering materials keeps us cozy, and we'll uncover a really weird case where insulation can actually make things worse. After that, we'll totally flip the script and see how to get rid of heat with fins. And finally, we'll tie it all back to the world you see every day. All right, let's start with a classic scenario. It's a freezing winter day, you've got the heat cranked up, and your house feels nice and toasty. But you just know that heat is constantly trying to escape. The real question is, how, right? Even when you've sealed everything up tight, that precious, expensive warmth is finding a way out. It's going right through the solid walls, the windows, the roof. To really get a grip on this, we need a way to think about how different materials fight back against that flow of heat. And here's where things get really cool. It turns out we can think about heat flowing in pretty much the exact same way we think about electricity flowing through a circuit. It's a fantastic analogy. The temperature difference between inside and outside, that's your voltage, the force that's pushing everything out. The heat flowing out, that's your current. And the most important piece for us today, the obstacles slowing it all down, that's what we call thermal resistance. So, every single material has a thermal resistance. It's just a number that tells you how good it is at blocking heat. And the formula here shows us two really simple ways to crank up that resistance. You can either make the material thicker, or you can pick a material with what's called low thermal conductivity. It's exactly why a thick, fluffy wool sweater keeps you warmer than a thin sheet of metal. Okay, so a single material has resistance. Got it. But our world is built on layers. Your clothes are layers, your walls are layers. So what happens when we stack different materials together, like in a modern high-tech window? Well, for heat to escape through a double-paned window, it's got to go on a whole journey. It has to fight its way from the warm air inside to the first pane of glass, then it has to push through that glass. Then it has to cross the air gap in the middle, which is tough, then push through the second pane of glass, and finally jump from that cold outer pane to the even colder air outside. Each one of those steps is its own little obstacle, its own resistance. And just like in an electrical circuit, they all add up. And the effect of adding them up is, well, it's dramatic. Look at this. A single pane of glass in this scenario just bleeds heat, losing 266 watts. But watch what happens when we just add one more pane of glass and a little air gap. The heat loss plummets to just about 69 watts. That's a nearly 75% reduction in heat loss, all because that trapped layer of air is a fantastic insulator. But here's the thing. It's not just about saving energy. That extra resistance also means the inside pane of glass stays way, way warmer. Instead of being a frosty -2 degrees Celsius, it's a much more comfortable 14 degrees. And that is exactly why double-pane windows don't feel like a block of ice to the touch, and they don't get all fogged up with condensation on a cold morning. So, this all seems pretty simple, right? More layers, more insulation, less heat loss. It's always a good thing. But what if I told you that's not entirely true? What if, in some very specific cases, adding insulation can do the exact opposite? It sounds completely backwards, I know, but yes, it's possible. For certain shapes and sizes, wrapping them in insulation can actually help them lose heat faster. Let me show you how that works. This bizarre little phenomenon is called the critical radius. See, when you insulate something skinny, like a thin pipe or a wire, you're actually starting a battle between two different effects. On one hand, you're adding insulation, which, well, it resists heat flow, that's what it does. But on the other hand, you're making the whole thing bigger, which increases its surface area. And a bigger surface area makes it easier for heat to escape into the air. With really thin objects, that second effect, the bigger surface area, can actually win the fight, causing more heat to leak out. So does this mean you should run out and rip the insulation off your pipes?
Absolutely not. For the kinds of insulation you use in a building and for pipes in your home, this critical radius is tiny. We're talking about a centimeter at most. Any pipe in your wall is going to be way bigger than that, so adding insulation will always help. So here's the real-world takeaway. For big things, like your hot water pipes, go ahead, insulate away, more is better. But for something really thin, like an electrical wire, that plastic coating around it is often inside this critical radius, which means kind of secretly, it's not just protecting the wire, it's also acting like a mini cooling fin, helping that wire shed heat so it can operate safely. And for a wire, that's exactly what you want.
This actually leads us perfectly into our next idea. So far, we've been obsessed with blocking heat, keeping it in. But what if you want to do the exact opposite? What if your whole goal is to get rid of heat, and as fast as you possibly can? Believe it or not, nature figured this one out millions of years ago. A lot of scientists now think that the huge, bony plates on the back of a stegosaurus weren't just for show. They were probably full of blood vessels and acted like giant natural car radiators, cooling fins to help it regulate its body temperature.
And we use the exact same idea today, just engineered a little differently. Fins are just extensions that we add onto a surface to massively increase the area that's available for heat to escape. You see them everywhere once you start looking. On your car's radiator, on the engine of a motorcycle, on the heat sink cooling your computer's brain. The goal is always the same. More surface area means faster cooling. Simple as that. And designing a good fin comes down to a few basic rules. First, you want a material that moves heat easily, like aluminum or copper. The main goal is to get as much surface area as possible, which is why a whole bunch of thin fins works way better than just a few thick ones. And of course, you got to make sure those fins have a really solid connection to the hot surface you're trying to cool down.
So we've talked about resistance, layering, that weird critical radius, and cooling fins. These are not just abstract ideas from a textbook. They are actively, right now, shaping the world around you, especially the technology you buy and use every single day. For instance, the next time you're at the hardware store and you see a big roll of R13 insulation, you'll know exactly what that means. That R is for R value, and it is the exact same thermal resistance we've been talking about this whole time. And this chart shows you why something like glass fiber is such a great choice for insulation. It's got a nice high R value. Brick, on the other hand, not so much. So let's just quickly recap the big ideas. First, thinking about heat flow like an electrical current with resistance is a super powerful mental model. Second, layering materials, like in a good window, adds all their resistances together to become a really effective heat blocker. Third, remember that more insulation isn't always better, especially for very thin wires. And finally, if you need to cool something down fast, fins are your best friend because they crank up the surface area. The thing is, once you start to see this invisible flow of heat, you can't unsee it. You'll see it in the cooling fins on a motorcycle engine, in the layers of your winter coat, in a sleek design of your phone that's trying to dissipate heat while it's charging. These principles of thermal resistance, they are quietly and powerfully shaping our technology, our comfort, and our world every single day.